Collision. To configure collision between game objects in Unity, you need to use colliders. Colliders define the shape of a game object for the purposes of physical collisions. You can then use these colliders to manage collision events. You can configure collisions via collider components or the corresponding C# class. And pretty much we are inside physics, build and 3D physics collisions, and in the previous video we saw how to create a vehicle with wheel colliders, and this is pretty much the link. We use the C#, and if you go into the software, this is pretty much how it should look like. So we have the car root, or underscore root, as the parent. We have the cube as the child, and we also have the wheels as a child of the car underscore root parent. And then we have the front left, right, left, and we go into the wheels and to the car root. We are also using the rigid body here. As you can see, we have the simple car controller script. This is in C#. Okay, so we have all that, and let's continue here with the collision. So pretty much we have the main topic and the description real quick. So introduction to collision, how collision works in Unity, collisions, continuous collision detection, how to detect and handle collisions between fast moving objects in Unity, physics debug visualization, how to inspect the collider geometry across your scene and profile common physics based scenarios, configure wheel colliders for a vehicle, a walkthrough tutorial for configuring wheel colliders on a 4-wheel device, so we already saw that. Box collider component reference, so reference for the box collider component, capsule collider component reference for the capsule collider component. Then we have the terrain collider component, the wheel collider component reference, mesh collider component reference, sphere collider component reference, and finally the physics material component reference. So right now we are gonna see the first one, introduction to collision. So we're gonna go over this here real quick. So Unity handles collision between game objects with colliders, which attach to game objects and define the shape of a game object for the purposes of physical collisions. A collider is invisible and does not need to be exact the same shape as the game object's mesh. A rough approximation of the mesh is often more efficient and indistinguishable in gameplay. The simplest and least processor-intensive colliders are primitive collider types. And 3D, these are the box collider, sphere collider, and capsule collider, pretty much. If we go here, we have pretty much a cube, but if you go into the game object, if you go 3D object, you have the cube, the sphere, capsule, cylinder, plane, quad. So we have all that. Okay, so you can add any number of these to a single game object to create compound colliders. Compound colliders approximate the shape of a game object while keeping a low processor overhead. To get further flexibility, you can add additional colliders on child game objects. For instance, you can rotate the axis relative to the local axis of the parent game object. When you create a compound collider like this, you should only use one rigid body component placed on the root game object in the hierarchy. Primitive colliders do not work correctly with shear transforms. If you use a combination of rotations and non-uniform scales in the transform hierarchy so that the resulting shape is no longer primitive shape, the primitive collider cannot represent it correctly. Mesh colliders. There are some cases, however, where even compound colliders are not accurate enough. In 3D, you can use mesh colliders to match the shape of the game objects mesh exactly. In 2D, the polygon collider 2D does not match the shape of the sprite graphic perfectly, but you can refine the shape to any level of detail you like. These colliders are much more processor intensive than primitive types, so use them sparingly to maintain good performance. Also, a mesh collider cannot collide with another mesh collider. Nothing happens when they make contact. You can get around this in some cases by marking the mesh collider as convex in the inspector. Okay, this generates the collider shape as the convex hole, which is like the original mesh but with any undercut fill-in. The benefit of this is that convex mesh collider can collide with other mesh colliders, so you can use this feature when you have a moving character with a suitable shape. However, a good rule is to use mesh colliders for seeing geometry and approximate the shape of a moving game object using compound primitive colliders. And then we have the static colliders. Okay, you can add colliders to a game object without a rigid body component to create floors, walls, and other motionless elements of the scene. Okay, these are referred to as static colliders. We have the physics material. Okay, this is important. When colliders interact, their surfaces need to simulate the properties of the material they are supposed to represent. For example, a sheet of ice will be slippery while a rubber ball will offer a lot of friction and be very bouncy. Although the shape of colliders is not deformed during collisions, the friction and bounce can be configured using physics materials. Getting the parameters just right can involve a bit of trial and error. A slippery material like ice, for example, has zero or very low friction. A grippy material like rubber has a high friction and near perfect bounciness. So, see the reference page for the physics material and physics material 2D for further detail. Okay, now we have also triggers. The scripting system can detect when collisions occur and initiate actions using the onCollision enter function. However, you can also use the physics engine simply to detect when one collider enters the space of another without creating a collision. A collider configured as a trigger using the S-trigger property does not behave as a solid object and will simply allow other colliders to pass through. When a collider enters its space, a trigger will call on the onTrigger enter function on the onTrigger object script. Then we have the collisions callback for scripts, collider interactions, static collider, rigid body collider, kinematic rigid body collider, collision actions matrix. Here we have collision detection occurs and messages are sent upon collision. So here we have the static collision, rigid body collision, kinematic rigid body collider, static trigger collider, rigid body trigger collider, kinematic rigid body trigger collider. Okay, so we have trigger messages are sent upon collision. Okay, let me see. Now we're gonna see the continuous collision detection, so the CCD. Continuous collision detection, the CCD ensures that fast-moving bodies collide with objects instead of passing or tunneling through those objects. Unity provides the following CCD methods: sweep-based CCD and speculative CCD. To use sweep-based CCD, select a rigid body in the inspector. Okay, so again here we have, let me see, we go into the car route. Here we are using the rigid body. And what else do we have here? Properties. Okay, and here in the inspector window, set collision detection to continuous or continuous dynamic. For speculative CCD, set the collision detection to continuous speculative. So we can go in the inspector window and set the collision detection to continuous. So let me see, if we go into the inspector window and static now, and we can go into the set collision detection to continuous. Collision detection right now is discrete, but we can pretty much change it to continuous. Okay, so we have changed it to continuous right now, and let me see if this changes something. So let's play this game. And okay, so now this is continuous. And okay, I'm gonna go back here, gonna move, so nothing is changing so far. Okay, so I can rotate this object. I can pretty much move forward, and now I'm gonna pretty much going backwards. Let me see if we can still going backwards. Okay, so there you have it. Let's click, and okay, right now it's not playing. We have the collision detection set to continuous. It was before in discrete. We can set it also to continuous dynamic and continuous speculative. Okay, so let's continue. Sweep-based CCD. Sweep-based CCD uses a time of impact, so time of impact TOI algorithm to compute potential collisions for an object by sweeping its forward trajectory using its current velocity. If there are contacts along the object's moving direction, the algorithm computes the time of impact and moves the object until that time. The algorithm can perform sub-steps from that time onwards, computing the velocity after the TOI, the time of impact, then resweeps at the expense of more CPU cycles. So, however, because this method relies on linear sweep, it ignores the body's angular motion, which can cause tunneling effects when objects are rotating at speed. For example, the flipper in a pinball machine is fixed at one end and rotates around a fixed point. The flipper only has angular motion and no linear motion, therefore it can easily miss the collision with a pinball. So here they give us an example. So here we have this pinball here, a thin stick game object with its continuous dynamic property enabled. When rotating quickly around the pivot point, the stick doesn't make contact with the sphere. As you can see, it's not making any contact. Okay, so another issue with this method is performance. If you have a large number of high-speed objects with CCD in close proximity, the CCD overhead increases quickly because of the extra sweeping, and the physics engine has to perform more CCD sub-steps. Speculative CCD works by increasing an object's broad phase axis, allowing minimum bounding box AABB based on the object's linear and angular motion. The algorithm is speculative because it picks all potential contacts during the next physics step. All contacts are then fed into the solver, which makes sure that all contact constraints are satisfied so that an object does not tunnel through any collision. The following diagram shows a sphere moving from T0, so this is the sphere moving from T0. Could have an expected position at T1, so this is the T1 here. Okay, if there were no walls in its path, by inflating the AABB with its target pose, the speculative algorithm picks up two contacts with the N1 and N2 normal. So this is the N1 normal and N2 normal. So this is a little bit of physics, a little bit of mechanics. The algorithm then tells the solver to respect those contacts so that the sphere doesn't tunnel through the wall. So this pretty much are the walls right now, the N1 and the N2. Okay, inflated AABB based on current velocity helps detect all potential contacts along the moving trajectory, which enables the solver to prevent tunneling. Speculative CCD is generally cheaper than the sweep-based method because contacts are only computed during the collision detection phase, not during the solving and integrating phase. Also because speculative CCD expands the broad phase AABB based on the object's linear and angular motion. It finds the contacts that sweep-based CCD can miss. So now we have pretty much the same example, but this time there's contact here. Okay, so a thin stick game object with speculative CCD enabled. When rotating quickly around the pivot point, the stick makes contact with the sphere and a collision occurs. So maybe it's moving too fast here, but pretty much there is contact and a collision occurs. However, speculative CCD can also cause collision where an object's motion is affected by a speculative contact point when it shouldn't be. This is because speculative CCD collects all points contact based on the closest point algorithm, so the contact normal is less accurate. This can often make high-speed objects slide along the slated collision features and jump up even though they shouldn't. For example, in the following diagram, a sphere starts at T0, so it starts here at T0 and moves horizontally towards the right. So it's gonna move horizontally towards the right with a predicted position at T1. So after integration, an inflated AABB overlaps the boxes B0 and B1, so it's gonna overlap these boxes B0 and B1. Okay, and the CCD yields two speculative contacts at C0 and C1. C0 and C1. Okay, because speculative CCD generates contacts using the closest point algorithm, C0 has a very inclined normal, which appears to be a ramp to the solver. So 0, as you can see, has a very inclined steep ramp. Okay, the solver assumed that the contact point C0 is a ramp because the closest point algorithm generated an inaccurate contact normal. Okay, such a very inclined normal causes T1 to jump upward after integration rather than moving straight forward. So, and here they are using pretty much they're using the game here, not the scene but the game, and this is the example that they're giving us. So it's moving pretty much it's moving straight forward. Okay, a ghost collision generated at C0 causes the sphere to erroneously jump up instead of move straight forward. And here they also give us a similar example. Okay, so this one is the sphere inflated AABB using speculative CCD, which only computes contacts during the collision detection phase, so tunneling may occur. So here we have the, what is it, BB, and okay, so speculative CCD can also tunneling because speculative contacts are only computed during the collision detection phase. During contact solving, if an object gains too much energy from the solver, it may end up outside the initially inflated AABB. After integration, if there are collisions just outside the AABB, the object will tunnel right through. For example, the following diagram shows a sphere is moving left from T0, so it's from T0 here, it's moving left, while a stick is rotating clockwise. Okay, if the sphere gains too much energy from the impact, it may end up existing in the exiting the inflated AABB red dotted rectangle. So this one. Okay, at T1, so at T1 here, this is because the solver only computes contacts inside the inflated AABB, and collision detection isn't performed during the solving and integrating phase. So pretty much this is all that we have for the sweep based CCD and pretty much the continuous collision detection CCD.